The secret to a flawless Formula One Grand Prix isn't just about the speed of the cars, the precision of the drivers, or the brilliance of the engineering teams. It also comes down to something far less visible, something embedded deep within the very surface of the racetrack that most fans will never notice. Beneath the roaring engines, screaming tires, and cheering crowds lies a hidden network of wires, carefully laid and meticulously positioned. These aren't ordinary wires. They are part of an intricate system responsible for one of the most vital operations in motorsport. Imagine a Formula One car flying down the straight at nearly 200 miles per hour. While the action dazzles on the surface, underneath, this hidden technology is hard at work. Formula One circuits are literally cut open and rewired with purpose. But why go to such lengths just to insert wires into a track? What do these discrete lines actually do? The answer reveals an extraordinary fusion of speed, accuracy, and invisible engineering brilliance. Before a Formula One car can even roll out of the garage and put in a flying lap, something quietly but crucially happens behind the scenes. Specialized sections of the racetrack are cut open, not for maintenance, not for drainage, but for installation. Thin trenches, just about a centimeter deep, are carved across the tarmac. Full-width slashes that span from one side of the track to the other. These aren't random. They are meticulously mapped, and within those cuts, a loop of wire is embedded. Once the wire is set, the groove is sealed with a black silicone compound that camouflaged it perfectly with the track surface. On race day, most fans watching from the stands or even from home wouldn't see a thing. But those wires, they are essential. Without them, no official timings could be captured, no leaderboard would function correctly, and no reliable performance data could reach the teams. So what are these embedded wires really doing? They're part of what's called the timing loop system. It's a concept similar to what's used in traffic counter systems on highways. But in Formula One, it's far more advanced. The wires themselves are essentially acting like aerial receivers. As each car passes over them, these loops pick up a signal from a device inside the car. This device is known as the transponder. Every Formula One car is equipped with a transponder, and it carries a unique identification number. When a car crosses a timing loop, the loop reads this ID and logs the exact time it crossed. This happens at over 30 different points around a typical Formula One circuit, including the pit entry and exit. Each of these timing loops works like a digital checkpoint, ensuring that the flow of data is uninterrupted as the race progresses. The moment the transponder signal is picked up, it's converted into raw data and sent through the circuit's underground fiber optic network. That data doesn't just sit in a database, it's processed in real time and shared with the teams, race control, and even broadcasters. It's what allows those slick on-screen graphics to show precise gap times, sector performances, and real-time leaderboards. Unlike standard traffic loops, which might only count vehicles, Formula One's system is layered with intelligence. The loops can distinguish between different cars, not just by team, but by individual chassis ID, thanks to the unique signature sent out by each transponder. This also helps eliminate confusion when cars are close together, like during pit stops or formation laps. Some loops are positioned to mark the start and end of critical sectors on the track, breaking each lap into detailed segments. This allows engineers to dissect performance corner by corner, identifying exactly where a driver is gaining or losing time. It's not just about overall lap time, it's about how that time is built. During practice and qualifying, the data from these loops becomes especially vital. Teams can compare sector data across different laps, tire compounds, and fuel loads. It's like watching a race through a microscope. Every loop offers another lens into performance. Interestingly, the loops are embedded with such precision that they're aligned to within a few millimeters across the track surface. If they weren't, the entire timing system could drift out of sync, especially on high-speed straights where a car crosses the loop in a blink. Installation of these loops is done with military-grade precision. Track engineers have to measure, cut, and seal the loop into the tarmac in a way that doesn't interfere with tire grip or car handling. The surface has to be flush so there's no disruption to the driving line, especially in corners where every inch of track matters. Even wet weather performance of the loops is accounted for. The silicone sealant used is resistant to water intrusion, heat, and pressure, ensuring the data connection remains reliable no matter the conditions. Timing loops are also used to measure delta times during virtual safety car VSC periods. Drivers are required to stay within a target delta, and it's these loops that confirm compliance or detect violations. In close finishes, those heart-pounding moments when two cars cross the line side by side, these loops are what determine the result to the thousandth of a second. There's no human guesswork involved, only clean digital proof. The signal from the transponder is passive. It doesn't emit anything unless it's triggered by the loop. That trigger is electromagnetic, and it activates the transponder momentarily just as the car passes overhead. This system is standardized across all FIA-sanctioned tracks, which means whether it's Monaco's tight street circuit or Monza's flat-out straights, the data fidelity remains consistent. Each loop is calibrated before every race weekend. Technicians walk the track, check each connection, test signal strength, and verify accuracy using dummy cars or diagnostic tools. The entire timing system is double redundant, meaning that if a wire is damaged or a loop fails, a backup system immediately takes over without any loss of data. Teams often use the timing loop data to run simulations during the race. They plug the live sector times into predictive models to estimate fuel use, tire degradation, and possible overtaking windows. Because timing loops detect exact crossing times, they also help enforce track limits. If a driver cuts a corner and crosses a loop earlier than physically possible on a valid racing line, race control is immediately alerted. In wet races, these loops are often the only accurate tool for monitoring consistent lap times, as GPS and visual tracking can become unreliable due to visibility or spray. These loops are also used in post-race analysis, helping the FIA examine incidents, compare driver behavior, and assess whether a rule was violated based on timing irregularities. During red flag situations, the loop immediately records the position of every car at the moment of the stoppage. That's how officials determine grid order for restarts. Interestingly, the signal emitted by the loops only travels upward by design. This minimizes interference and ensures that only the car directly above the loop is detected, not those nearby. In multi-class events like endurance races or support races on the same weekend, these loops help distinguish between vehicle categories sharing the same track. Some circuits embed extra loops in high-risk zones like chicanes or pit lane entry to get a tighter resolution on driver inputs and cornering behavior. During pit stops, engineers compare entry and exit times using the loops to measure turnaround time down to the hundredth of a second. Even slight hesitation by a driver can be analyzed. The loops are laid symmetrically across the track so that no matter which racing line a driver takes, tight inside or sweeping outside, their time is recorded at the exact same point. Each loop is tested under load, meaning it's not just scanned empty, but with moving vehicles to simulate actual race conditions. Modern F1 circuits often build the loops into the track during resurfacing or renovation, ensuring better durability and integration with future technology upgrades. Finally, while spectators rarely see the loops themselves, anyone watching closely at track level might spot a faint black line cutting across the asphalt. That's the gateway to every piece of timing magic seen during a race. Now, the timing transponder isn't just tossed anywhere inside the car. According to the FIA, the global governing body for motorsport, it can be placed in 3 approved locations, referred to as Position A, Position B, and Position C. In practice, most teams choose to install the transponder at Position C, which is located near the rear axle. Why Position C? It's a central and stable location that's less prone to interference or movement, which means it gives the most consistent timing data. But this transponder isn't alone. 2 other components work alongside it: a GPS beacon, and an identification beacon. So now the question arises, why not just use GPS for everything? After all, satellite navigation systems are used in smartphones and even by amateur runners to track laps. The answer is simple. GPS alone just isn't accurate enough for Formula One. The sport demands split-second precision. GPS signals can fluctuate, especially with multiple cars in close proximity and high-speed movement. In F1, even a millisecond matters. The GPS beacon, typically mounted near the driver's head in position A or B, gives a general sense of where the car is. It helps provide a bird's-eye view of each car's path on track. But it cannot be relied upon alone to log precise crossing times. That's where the transponder and the timing loop dominate. GPS, for all its brilliance, operates on a system that was never designed for millimeter-level accuracy at 300 kilometers per hour. It's great for mapping out a driver's route or showing general position on a race map, but it lacks the granularity that Formula One demands. One of the biggest issues is signal delay. GPS relies on satellites orbiting thousands of kilometers above Earth, and while the data exchange is fast, it's not instant. In a sport where cars move the length of a football field in less than a second, even a tiny lag matters. There's also the issue of signal congestion. When 20 cars are all navigating through tight hairpins, under grandstands, or through urban sections like Monaco, GPS signals can become disrupted or even bounce off nearby buildings. This phenomenon, known as multipath interference, causes positional errors that are unacceptable in elite motorsport. And then there's weather. Heavy cloud cover, rain, or electrical interference can slightly degrade GPS accuracy, something unthinkable in a sport where stewards hand out penalties based on millisecond-level infractions. Even with differential GPS systems, which use ground stations to improve accuracy, it's still not perfect. The transponder and timing loop system, in contrast, offers a closed-loop environment. It doesn't rely on external satellites or atmospheric conditions. Everything is grounded, self-contained, and controlled. The data isn't just accurate, it's consistent. That consistency is what engineers crave. A data stream that never wavers means reliable decision-making during high-pressure scenarios. And consistency matters in strategy too. When a team decides whether to undercut or overcut another car in the pit window, they're relying on real-time delta data. If GPS were off by even half a second, the call could backfire completely. That's the kind of risk no strategist is willing to take. The transponder system also works brilliantly in congested environments. In wheel-to-wheel racing, two cars could be separated by mere centimeters. GPS might register them as overlapping or even swap their positions momentarily. The timing loops, however, know exactly when and where each car crosses, even if it's just the front wing tip ahead. Another challenge GPS faces is vertical accuracy. While horizontal location can be fairly precise, vertical position, knowing the exact height of a car, is more variable. This might not sound like a big deal until a car goes up a hill or into a dip. On undulating circuits like Spa-Francorchamps or Austin, this difference can confuse GPS-based location readings. The FIA also needs a system that can withstand fail-safes. With GPS, any issue with satellite communication could throw off half the grid. But with a network of ground-based timing loops and beacons, redundancy is built into the system. If one loop fails, others fill in. It's not just about being accurate, it's about never going dark. Teams also need to compare driver performance across corners with extreme detail. The slight lift before a high-speed turn, the micro-adjustment into a braking zone, all of this is logged and analyzed through the timing loops. GPS just can't offer that level of frame-by-frame clarity. Another factor is refresh rate. Most consumer GPS devices update location once per second. Formula One's timing system does it every fraction of a second. It's practically real-time telemetry. That level of resolution is critical when cars are traveling nearly 90 meters every second. Then there's security. Satellite signals can be jammed or spoofed. In F1, where teams invest hundreds of millions into performance, even the smallest glitch could cause chaos. The transponder system is hardened against external tampering. Its infrastructure is tightly regulated, monitored, and localized. Let's not forget how the transponder integrates into other systems. It syncs with pit stop analysis, jump start detection, VSC delta monitoring, and safety car protocols. GPS simply doesn't hook into that network as cleanly or reliably. Even the safety car depends on the transponder timing loop system to guide its positioning during neutralized race periods. It's not just about knowing where the cars are, it's about knowing precisely when to enter, pace, and exit the circuit to maintain race integrity. Broadcasters also rely on accurate car positioning to render virtual graphics during the race. Ever seen the side-by-side comparisons or predictive overtakes shown on screen? Those don't come from GPS, they come from the transponder and loop network tracking the cars with uncanny precision. Teams feed all this data into AI-driven simulators during the race. Algorithms predict tire wear, fuel usage, and overtaking probabilities. The cleaner the data, the better the predictions. The margin for error is razor thin. With over 30 timing loops around the track and transponders that ping with perfect regularity, the system is fine-tuned for endurance. From Friday practice to Sunday's final lap, the accuracy never fades. Even during formation laps or safety car restarts, knowing exactly where each car is, down to the centimeter, is critical. GPS simply can't guarantee that. While GPS will always play a role in giving a macro view of the race, it's the transponder timing loop system that builds the foundation of fairness, accuracy, and reliability in Formula One. So while most fans see only the surface, the cars, the noise, the speed, beneath that spectacle is a web of technology working overtime to make it all trustworthy. The transponder and timing loops are the unsung heroes, ensuring that no moment, no movement, and no millisecond is ever lost. The identification beacon adds another layer of redundancy. If for any reason the transponder fails or isn't detected, this beacon acts as a backup identifier. It helps race control distinguish whether the vehicle is a Formula One car, a Formula 2 car, the safety car, or the medical car. This may sound like a minor detail, but in high-pressure moments like a safety car deployment, knowing exactly which car is where can be vital. This beacon also ensures continuity if anything goes wrong with the main system during a race. All of this advanced equipment would be useless without a way to get the data off the track and into the hands of the decision makers. That's where the fiber optic cable network comes in. Across each Formula One venue, there are roughly 36 miles, yes, miles of fiber optic cable. These cables act as the digital nervous system of the track. They don't just transmit the timing data, they carry live video, real-time audio, and communication between marshal posts and race control. It's a total data pipeline. The infrastructure is massive and complex, yet it's also ultra-reliable. Each track has 12 trackside nodes, which act like central hubs. These nodes receive raw signals from timing loops, cameras, and other devices, decode them, and forward that information to central race servers. From there, the data is disseminated to teams, broadcasters, the FIA, and the control room, and it doesn't stop with the on-track setup. Redundancy is a critical part of the system. Every trackside component, whether it's a timing loop, a beacon, or a node, operates with its own power supply. This means if there's a power outage somewhere on the circuit, these systems remain functional. Just a few weeks ago, there was an incident where the FIA's trackside CCTV system went down due to a power issue. But thanks to these independent power systems, the race wasn't compromised. The broadcast cameras kept rolling and the timing data kept flowing. Another fascinating function of the timing loop system is how it detects jump starts. If a driver moves even slightly before the lights go out, it's picked up instantly. Here's how it works. Within every grid slot, there are small metal holes embedded right in the center. These holes are filled with detection beacons that emit a cone-shaped signal, which fans out in a kind of invisible funnel above the surface. The transponder in the car, when positioned correctly over this detection zone, remains in range. If the car starts moving forward even just a few centimeters and crosses out of that detection field before the official start signal, it's flagged as a jump start. This detection zone is precise but not foolproof. There's a small buffer zone, enough that a car might inch forward slightly and still remain within the detection field. That's why sometimes drivers appear to have moved before the lights went out but aren't penalized. However, if the transponder isn't working, the system can't detect movement at all. This was seen in the 2020 Austrian Grand Prix when Lewis Hamilton was suspected of a jump start, but no penalty was issued because the transponder failed. Without that signal, there's no proof. But of course, a faulty transponder is a double-edged sword. Yes, the driver avoids a penalty, but they also lose access to live timing data, which can be a huge disadvantage in race strategy. Timing transponders also play a major role in one of Formula One's most underrated battlegrounds, the pit lane. Pit stops are measured not just in seconds, but in hundredths of a second. The clock begins ticking the instant a car crosses into the pit lane and stops the moment it exits. How does the system know when this happens? By using the same technology, timing loops and transponders. As the car enters, it passes over a timing loop. The transponder signal is detected, and the system logs the entry time. When the car leaves, another loop picks up the signal again, and the exit time is recorded. The difference is the pit stop duration. What's even more impressive is that these loops are spaced out every 200 meters or so, creating what's called mini sectors. These mini sectors break down the pit lane into smaller segments, which means teams can analyze not just how long a car spent in the pit lane overall, but how it performed in each specific segment. Was the driver too slow on approach? Did they hesitate on exit? Did the crew perform optimally? For example, during the 2019 Brazilian Grand Prix, Lewis Hamilton's pit stop was clocked at just 1.83 seconds. That's faster than boiling water in a microwave. And the timing transponder was essential in capturing every fraction of that time with surgical accuracy. Trilateration plays a role here too. That's the process of using multiple beacons to determine a car's exact location in the pit lane, even if it's not directly over a single timing loop. It's similar to how GPS triangulation works, but with much finer resolution. This method ensures that no matter where the car is in the lane, even if it's nudged slightly to one side, the system knows exactly when it enters and exits, preserving the integrity of the pit timing. Across an entire race weekend, all of these systems work together to provide not just timing, but real-time telemetry, positioning, and identification. They ensure fair play, track safety, and fan engagement all at once. From a viewer's standpoint, watching a lap time pop up on screen seems instantaneous and effortless. But behind that moment is a complex ballet of technology, regulation, and infrastructure. Even support series like Formula 2 use the same setup, and so do the safety and medical cars. Consistency across all vehicles ensures no confusion when analyzing incidents or deploying emergency services. This uniformity means that whether it's Max Verstappen leading the pack or the safety car managing a yellow flag period, every vehicle is accounted for and logged with identical precision. So why go through all of this trouble? Why not stick with older, simpler systems? The answer lies in what Formula One has always represented: engineering at the edge of possibility. The sport isn't just about cars, it's about information. A millisecond's delay in data can change pit strategies, affect tire choices, or influence overtakes. Real-time access to data isn't a luxury in Formula One, it's the baseline standard. And while the roar of the engines and the spectacle of wheel-to-wheel combat might steal the show, it's the invisible network of wires beneath the track and the electronics within the car that truly make modern Formula One possible. They're the digital backbone that keeps the sport fair, fast, and transparent. In many ways, the circuits themselves are living systems, nerve endings layered with sensors, receptors, and data pathways. And the wires buried beneath the surface? They are the veins, carrying lifeblood information that fuels the heartbeat of Formula One. If this behind-the-scenes glimpse into Formula One technology fascinated you, don't forget to hit that like button and subscribe for more deep dives into the engineering magic of motorsport. Turn on notifications so you never miss an episode, and if you want to experience the thrill of F1 live, check out the link in the description for discounted tickets to upcoming races. See you at the next Grand Prix.